The Doppler effect was discovered in 1842 by Christian Doppler. But in order to understand the Doppler effect, we need to know a little bit about waves first. So, one way to distinguish different waves from each other is by their wavelength. A wavelength is a measure of the distance between two successive corresponding points on a wave. So, as you can see, there's different points you can pick on the wave. This can be either from crest to crest, trough to trough, null to null, or just any point in between, as long as they're both corresponding and right after each other. The frequency of a wave is the amount of waves that pass a certain point in a given amount of time. So as you can see, the top wave in this picture is much more frequent than the bottom wave because in the same amount of time, it produces much more waves. It is important to note that frequency and wavelength are indirectly related. So the higher the frequency, the shorter the wavelength is going to be, as you can see in the top picture, and the lower the frequency, the longer the wavelength is going to be in the lower picture that shows it. So they're related by the equation velocity equals frequency times wavelength. So knowing the velocity of a wave and a frequency of the wave, you can solve that for wavelength, or you can solve for frequency just by what you know. So now that we have an understanding of waves, what is the Doppler effect? It is a shift in a wave's frequency due to the source or an observer moving. Here is a video that shows the Doppler effect. So what you should have noticed in the video is that the car had a higher pitch as it was approaching, and as it was leaving, it had a lower pitch. To show this in a visual, let's just say this truck is just sitting here and honking its horn, and each of these lines around it represent a wavelength. So as you can see, all of the waves are evenly distributed now that the truck is still. But if the truck starts moving to the right, it is almost like crushing the waves in front of it, making their wavelength shorter, and the back ones compensate for it, giving them a longer wavelength, or also known as a lower frequency. To solve for how much the frequency of the wave is shifted, we have this equation, and you just plug in the values that you know to solve for it. So f of 0 is going to be the frequency that you observe due to the shift. The f of s is going to be the actual frequency. V is just going to be the velocity of the sound or of the wave. V sub 0 is going to be the velocity of the observer. V sub s is going to be the velocity of the source. And the signs are there because it can be positive or negative depending on the direction that the observer or the source is moving. So I'm going to explain that more on the next slide. So to know what sign to use, you kind of have to think about it. Whenever something is moving away, you need to use the sign that will make the frequency lower. And when something is moving towards you, you need to use the sign that is going to result in a higher frequency. Since the velocity of the observer is on the top of the equation, when the observer is approaching, in order to make the frequency higher, you will add the velocity of the observer to the velocity of the wave. And if they are going away from the source, you will subtract the velocity of the observer from the velocity of the wave. The velocity of the source of the wave is on the bottom of the equation, so the opposite is going to be true. If the source is approaching, subtracting the velocity of the source from the wave's velocity is going to result in a higher frequency because you will end up dividing by a smaller number. And if the source is moving away, you will use a positive sign to make the frequency smaller because adding the numbers will result in a larger number that you are dividing by. So this slide shows the different scenarios and which sign to use when both the source and the observer are moving. But there can also be just the source or the observer moving, and in that case you would just put a 0 in for the velocity of what isn't moving, and the sign won't really matter since it's changing the velocity by 0 either way. Here is an example of a problem you may see. A train emits a sound at a frequency of 900 Hz. An observer in a car travels away from the source at a speed of 22 meters per second. What is the frequency heard by the observer? Assume that the speed of sound is 343 meters per second. So using the equation, I plugged in my values for the source and the observer. Since the observer is moving away, I used a negative sign, and this resulted in a fraction of 321 over 343. And by multiplying that fraction by 900, I ended up with 842 Hertz. Another example problem that you may see is a police car is chasing you at a speed of 60 meters per second. You are speeding away from the police at a speed of 69 meters per second. If the police car siren emits a sound at a frequency of 1800 Hertz, what frequency will you observe, assuming the speed of sound is 343 meters per second? So using the equation, I plugged in the values into their spots, and I used a negative sign on top because the observer is moving away. I used a negative sign on the bottom because the police car is moving towards. Solving this the rest of the way results in a frequency of 1742.76 Hertz, which makes sense when you think about it because you are moving away faster than the police car is moving towards you, so the frequency should be smaller, and it is. The Doppler effect not only affects sound waves, but it affects light waves as well. So red has a lower frequency than purple light, so when light is moving away, it will result in a red shift, and if it is moving closer, it will result in a blue or like a violet shift. I really like this picture because it demonstrates the Doppler effect really well in light waves. Something super cool is that scientists actually see a red shift in our universe today, which is proof that our universe is expanding. And I think it's super cool that we deal with so many things that are affected by the Doppler effect every single day. I hope that now that you know what the Doppler effect is, you can start to recognize it when you see it.